welcome to another module. We are deriving the LMMSE estimate of the channel coefficient in an OFDM system, that is considering each subcarrier. We are deriving the LMMSE estimate of the channel coefficient corresponding to that particular subcarrier, alright. So, across subcarrier L, right, we have YL equals HL, where HL is the channel coefficient times XL plus VL, right. VL is the noise corresponding to subcarrier L. We have seen that HL is basically such that assuming 0 mean IID taps of variance sigma L, IID channel taps of variance sigma H square each. We have seen expected value of HL is 0, the variance expected value of magnitude HL square equals L sigma H square. We have also seen, assuming IID Gaussian noise samples 0 mean of variance sigma square each, expected capital VL, the noise sample on each subcarrier, this is equal to 0, expected value of magnitude VL square, this is equal to, what is this equal to? This is equal to, well, n times sigma square. What is L? L equals the number, L is equal to number of channel taps and N is equal to number of subcarriers. Okay. This we have seen so far, we have seen, alright. Let us now assume that this channel coefficient HL and the noise VL are independent. So, we are going to assume that similar to what we have assumed before, that is the channel coefficient H, correct, the channel coefficient H that these channel coefficient and noise VL are independent. Okay. And we have already justified this several times before. We said the channel coefficient arises because of the properties of the ambient scattering environment. The noise arises because of the thermal noise process at the receiver, and these two phenomena are independent. Alright. Therefore, the channel coefficient and the noise can be assumed to be independent. Alright, that is a realistic and in fact a very practical assumption. Okay. So, we can say that expected value of HL times V conjugate L equals 0. In fact, expected value of VL times H conjugate L is also 0. Now, coming back to our model, that is YL equals XL plus VL, we can compute the MMSE estimate H hat of L as R HL. Remember, this is a standard expression, that is the cross covariance between HL YL into R, the covariance of YL inverse times YL. This is the standard expression. Remember, this is the LMMSE estimate of LMMSE estimate of the channel coefficient HL. Alright, this is R HL YL, which is the correlation alright, the correlation between HL and YL times R YL inverse, where R YL is basically the covariance of the output YL on the L subcarrier times YL, where YL is the output of the L subcarrier, alright. This is basically follows from the expression for the standard LMMSE estimate, alright, the principle of standard LMMSE estimation, alright. Now what remains is basically to compute each of these quantities R YL equals expected value of YL times Y conjugate L. This is equal to, well, substitute YL, expected YL is basically your HL XL plus VL times HL XL plus VL conjugate. This is equal to the expected value of, well, HL. Let us just write a couple more steps in between to be very clear. HL XL plus VL into H conjugate L X conjugate L plus V conjugate L, and now I can expand this as expected value of, well, HL. We have the first term HL XL H conjugate L X conjugate L, that is magnitude HL square magnitude XL square plus VL into H conjugate L H conjugate L into X conjugate L plus, well, plus HL XL into V conjugate L plus VL into V conjugate L, that is magnitude V conjugate magnitude VL whole square. And now I can simplify this as, well, term by term, taking expected value of magnitude HL square into magnitude XL square plus expected value of VL H conjugate L X conjugate L plus expected value of HL into V conjugate L into XL plus expected value of magnitude VL square. Now, we know that expected value of VL HL conjugate is 0, expected value of HL VL conjugate, this is 0, because the noise and the channel coefficient are uncorrelated. Expected value of magnitude HL square, this is L times sigma H square, this we already know, expected value of VL square is N times sigma X square. Therefore, what we have is L times sigma H square times magnitude XL square plus N times sigma square, that is your R YL YL, which is the covariance of, right, which is the covariance of the channel coefficient, which is the covariance of the channel coefficient Y, the observation YL across the on the Lth subcarrier, alright. And now we need to compute R HL YL, which is the cross correlation between the channel coefficient HL and the observation YL, okay, and that can be also be computed in a straightforward fashion as follows: R HLYL equals expected value of HL into YL conjugate equals expected value of HL times HL XL plus VL conjugate equals expected value of, well, HL into H conjugate L X conjugate L plus V conjugate L, which is equal to expected value of, well, magnitude HL square X conjugate L plus expected value of HLV conjugate L, which is 0, expected value of magnitude L conjugate H conjugate magnitude HL square is L sigma H square. So, this is simply L sigma H square X conjugate L, where remember XL is the pilot symbol transmitted on the or loaded on the Lth subcarrier. XL equals pilot symbol loaded on the Lth subcarrier. This is the pilot symbol. Remember, we transmit pilot symbols specifically for the purpose of channel estimation, and this is the pilot symbol that is loaded on the Lth subcarrier. Therefore, now substituting, therefore, we have computed both the quantities RHY and RYY. Now, substituting it in the expression for the LMMSE estimate, we have the LMMSE estimate that is given as H hat L equals R HL YL R YL inverse into YL. Now, R HL YL is L sigma H square XL conjugate into R YL inverse is basically into 1 over, where R YL is basically your that is basically your L sigma H square magnitude XL square plus N sigma square times YL, and therefore, now I can write this estimate as your H hat L equals, well, L sigma H square divided by L sigma H square plus L sigma H square into L sigma H square X conjugate L divided by L sigma H square magnitude XL square plus N sigma square into YL, that is the output on the Lth subcarrier. And if you look at this, this is the expression for the, once again, LMMSE estimate of HL. This is the LMMSE estimate of HL. And once again, you can see in this expression for the LMMSE estimate. So, we have derived the expression for the LMMSE estimate. You can see once again for the from the expression for the LMMSE estimate, that if at high SNR, again similar to at high SNR. What do we mean by SNR? Implies if L sigma h square magnitude XL square is much greater than n sigma square, then H hat L becomes approximately your, I can ignore n sigma square in comparison to L sigma h square magnitude XL square. So, this becomes L sigma h square, well, x conjugate L divided by L sigma h square magnitude XL square into YL, but x magnitude XL square is nothing but XL into x conjugate L. Therefore, this becomes, well, L h sigma h square, L sigma h square cancel. So, this becomes 1 over XL into YL, and this is simply the ML estimate, that is, this is simply the expression for the maximum likelihood ML estimate, that is once again at high SNR, that is when your L sigma h square magnitude XL square is much greater than the noise power n sigma square on subcarrier L, then what happens? It again reduces to the ML estimate, the maximum likelihood estimate for the channel coefficient HL, which is simply YL, that is the output on subcarrier L, divided by XL, which is the capital XL, which is the symbol loaded on the subcarrier L. Okay. Now, also we can again similarly find out what is the error, what is the variance of the error corresponding to the estimate of channel coefficient L. So, let us now complete this problem by finding the variance of the error. The error variance of LMMSE estimate for the OFDM system is, well, we have expected value of magnitude H hat L minus HL whole square, this is equal to R HL minus R HL YL into R YL inverse into R YL, well, HL. Now, if you can observe this quantity is what we have exactly computed above, that is R HL YL into R YL inverse is the quantity that we have computed for the already computed for LMMSE estimate. Okay. This is the quantity that we have already computed. Now, R HL this is nothing but expected value of your magnitude HL square, and this is equal to L sigma h square, and this quantity R YL is expected value of YL into HL conjugate, this is nothing but R HL YL conjugate. We have already computed R, and this is equal to basically R YL, that is basically your R YL HL is basically R, if you look at this quantity R YL HL, this is expected value of YL into H conjugate L, which is basically R HL conjugate into R HL YL conjugate. Okay. And we have computed all these quantities before, that is R HL YL, and each of these quantities we have computed before. So, all that remains is basically it remains to substitute these quantities, okay, which I am going to do now. So, R HL HL, that is basically your, let me write this again, R HL HL, that is equal to L sigma H square minus R HL YL into R YL YL inverse, that we already seen above, L sigma H square x conjugate L divided by L sigma H square magnitude XL square plus N sigma H square times R YL HL, which is R HL YL conjugate, that is L sigma H square x conjugate L conjugate, and therefore, that gives us L sigma H square minus L sigma H square magnitude XL square plus N sigma square times L sigma H square whole square into magnitude XL square, which is equal to L sigma H square into 1 minus L sigma H square magnitude XL square divided by L sigma H square magnitude XL square plus N sigma square, and this is equal to, well, if you look at this, this is simply your L sigma H square into L sigma H square magnitude XL square minus L sigma H square magnitude, this cancels. So, what is left is N sigma square divided by L sigma H square magnitude XL square plus N sigma square. Now, bringing L sigma H square and N sigma times N sigma square to the denominator, what we have is this is equal to 1 over 1 divided by, well, N sigma square divided by magnitude XL square plus 1 over L sigma H square, and this is basically your equals your expected value of magnitude H k H hat k minus H k whole square. Okay. So, what we get is this is equal to this quantity, this is the expression for the error variance, expression for error variance this is the expression for error variance of estimate, sorry, this has to be H hat of L, that is the estimate of the Lth subcarrier, yeah, magnitude H hat L minus H L square, expression for the error variance of estimate H hat L corresponding to subcarrier L. Alright. So, this is the expression for the error variance, the variance of the error of estimate H hat L corresponding to subcarrier L, and once again you can see 1 over L sigma H square is basically the prior variance, that is L sigma H square is basically the prior variance of HL, right, we have already seen that. N sigma square is basically N sigma square divided by magnitude XL square is the variance of the or the mean squared error of the maximum likelihood estimate. Therefore, again you can see it is the harmonic mean of the mean squared error of the maximum likelihood estimate and the prior variance, alright, and this is something that we have seen several times before, and once again well, this is true of all LMMSE estimation in general. So, this is basically your again to reconfirm that 1 by ML MSE plus 1 by prior variance. That is, this is basically equal to your the harmonic mean of maximum MSE of ML comma where ML denotes the maximum likelihood estimate, that is it is a harmonic mean of the mean squared error of the maximum likelihood estimate and the prior variance of the channel coefficient. Alright. So, basically this completes the LMMSE estimate of LMMSE estimation of the channel coefficient HL corresponding to subcarrier L, and also the derivation of the variance or the derivation of the mean squared error rather of the estimate of the LMMSE estimate. Alright. We will continue in the subsequent module. Thank you very much.